Welcome to part 2 of module 6 on data link layer. We're going to talk about the different topology, the physical and logical topologies. We've learned that the data link prepares data for the physical network. So it must know a little bit about what physical connections there are, but it also explains ways which the data link layer works in relationship to different logical networks. There are two basic type of topology, the way data or networks are organized. One is the physical topology, and it identifies all the physical connections, how devices are connected between the end device, intermediary devices, i.e. switches and routers and wireless access points. And usually you identify them in floor, I'm on floor 1, room 21, desk 15, so that you can understand where, if something broke, where you can go to get it. So you'd make sure you identified your devices in such a way that you remember you changed the host name of a switch or a router. You do that for this purpose, so that you knew where to get. If something was wrong, somebody had a question, you could look at it and say, oh, that's on the second floor, room 21. And then there's the logical topology. And basically that is how the network transfers frames from one node to the next. Because I don't have to go through the same route every single time based on devices being up and down and how much traffic they're getting. The network can decide a faster route. So sometimes it will not always follow the same destination, the same path to get from source to destination. So the data link layer looks at the different depths, because you got to go from between different parts, because you're looking at, you got switches, routers, but is this connection between these two, is that fiber? Is it an Ethernet cable? What kind of Ethernet cable? How fast is that Ethernet cable? All of those have a decision, or that has to take place in the device to put the physical signal on that cable, or airways, or lights, whatever the case may be. As it's going between all these devices, it's making those decisions port to port between individual devices. So one, I've got the physical topology, how are things wired in the room? I got the server room, IT room. I got, different shelves, different rooms, different classrooms, and they all go through a physical layout so that exactly where everything is wired. And hopefully you've got it labeled so that when you get into the server room, you're just not looking at a bunch of blue cables and don't know which one is, where is rack 2, shelf 1, port 4, where's it going? You want to make sure you label all your wiring in the cable room so that you know where you're going. And then you got the logical. Now, here it's like I'm on this network, so all these devices can communicate with each other. And then I've got multiple devices here, networks that they can communicate with everybody in their logical group for security purposes, for efficiencies, for speed, all of those things that you're going to logically group your data. Maybe you've got accounting not want to talk to management, or whatever the case may be. I want to make sure the warehouse doesn't get access to accounting information. So I want to make sure data is isolated. So you're going to logically organize it in a way that makes better sense as far as how to protect that data and to streamline or make the network a little bit faster. Now, there are several different types of wiring network topologies. One, you got point-to-point, and point-to-point's fairly straightforward. It's one end to the other, and you see this a lot in small networks that have just got two devices connected to each other. There is a hub and spoke, or in some cases you may hear a star network, where I've got a central device and it kind of acts as a control mechanism. So I can't get to any of these other. So if I want to get from this one to this one, I've got to go through the middle one. And then the third one is mesh. Now the mesh this is a fully mesh network, only from the standpoint that every device is connected to every other device. Very fast, very nice. Small networks, you can do this. Larger networks, cost prohibitive. You didn't want to do it. So it's just something to keep in mind that most of your networks are going to be mesh-like. Sometimes you may even heard the term partial net mesh, showing that I don't have it. It'll be a combination between a mesh on one end, leading into maybe a hub and spoke, and eventually going to a point-to-point maybe. So it'll change to go through. Now, on a point-to-point, basically it's just what? Connecting two nodes. Most of our networks and labs in this class will be a point-to-point connection, at least as far as routers are concerned. But you get larger networks where you talk to your ISP. Guess what? Your ISP controls tons of different devices. To you, it may seem like it's a point-to-point, but once you go out to the wide area network, you have a lot of other devices you can't control. Yeah, you think you're only connecting one to your ISP. That's fine. I mean, because they only give you one IP address, and you've got a MAC address, you've got their MAC address to get to that interface. But after that, there's a whole lot of other stuff going on, so it's not necessarily a point-to-point as far as anything else is concerned. Now, as far as a local area network, I mean, that's a wide area network. This is a local area network. There are several different types of ways it could be done. You saw a little bit of one up above where it had looked like a star. You may hear it called a star. You may call it an extended star, and really all that means is one of the spokes attaches to another center hub. Similar to this. You got a star like we've seen before. You got an extended star where one of these branches here connects to another star. And like I said, you're going to see a lot of that. You probably will see some what they call a bus topology, where this is kind of I've got all the data is going along one major cable, and then everybody else taps into it. Now, the disadvantage of this is a couple. One, if one of these breaks, I lose connectivity between all the ones at down one end. The star, if something breaks here, what do I lose? I only lose access to just that one piece. Extended star, based on what breaks, if this one breaks, I lose all of one network. But in this case, if I lose one network because I've only got one path, it goes through. The other thing with a bus technology, they have to be terminated. You see these black circles here, indicates that the signal has to be terminated. It actually has to get to the end and basically absorb that signal and not retransmit it. If you forget to put the termination on the end of the bus, your signal is going to do like a wave hitting a wall. It hits, and what did it do? It reflects back, and that signal goes back up, and you start adding a lot more data, a lot more garbage on the line. The other one is a ring topology, where you'll have to put, like what they'll say, they'll have a token, a baton in a relay race. Is an example that I can only put data on the network if I have that token, if I have that baton. So once I have the baton, I can put the data on, and it'll go all the way around. Of course, that means anybody else who wants to put the data on this network has to wait for that baton to be passed on to the next person. And there's a bunch of rules as far as how long you can hold the baton, how fast how much data you can put on it. Sometimes you'll hear of, you'll have dual rings, one going one way, one going the other, to kind of help augment, the speed of accessing data between different devices. So now I mentioned earlier about half duplex and full duplex. Basically, half duplex is like a walkie-talkie, one-way communications at a time. So you got two devices, and like I said, you've got to press play to talk, and press the button to talk, even though there's no buttons here. But I'm only hearing information one way. I send it, and I'm getting no answers back. In a full duplex communication, you've got data going in both directions simultaneously. That's the key. Now, when you're setting up switches and hubs, you have to say, what am I in, full or half duplex, so the other end knows which way, what communication path, rules are we going to use. Now, newer equipment has an auto detect, and it pretty much says, hey, let me test, do I have a half or full duplex connection between these two devices, and then I'll automatically send the data accordingly. Most of these equipment you're going to use today, unless it's really old, you're not going to care about duplex. But I can guarantee that you'll probably see an example on a test that why aren't two devices communicating, and you'll find one will be full duplex, one will be half duplex. If you got that situation, data will not transfer between the two. Now, the MAC address always says, okay, now I've got this data. I've got to put data on the media. And what that is access control. How do I get access to the media to be able to put data on it? There's two different types of data. There's contention-based, where I'll just put it up there, and if a problem occurs, if there's a collision of data that packets collide, then I'll just back off a little bit, wait a predetermined amount of time. Hopefully it's a random amount of time on both ends, so that we're not all trying to re-put data back on at the same time. Or there is I'm sensing data, but I'll put things in place to avoid a collision. And that's usually used for wireless networks, because wireless networks, you can't see who's potentially on your network. So you do everything you can to avoid a collision versus processing it when a collision happens. We talked a little bit about token rings, but there's a couple of different out there. There's a legacy token ring, and there's an ArcNet. There are multi-access networks. I'm not sure how much they're using it today, but just know you may come across it. Now, on this contention base, on this carrier sense, that's what this carrier sense, multiple access, collision detection. Now, collision detection just says, hey, if I receive a collision, if there is a collision, then I will decide to do something. It goes through all the different areas. It says you got a frame to send, you can go through all those. Now, on collision avoidance, and 802.11 uses that extensively, because it can't see all these devices. In a wired network, you know exactly who's connected to you. But in a wireless network, you don't know who's on, who's off. So you're going to go through and process information differently. You're going to ask for permission. You're going to get acknowledgement that, hey, is it free enough to go up there? You're going to get permission to send it. You're going to send it. You're going to be told that it's arrived. So it's a little bit different, but just know that collision avoidance is used in wireless networks, collision detection in a wired network, and hopefully that helps you understand a little bit about that. I'll let you take the little quiz, and I will come back and do part 3 of this lecture in the data link frame itself.